from you is that you want the basics as well. And a couple of you also wrote that no theory, please. But I'm sorry, but some theory has to be talked about, especially when you really want to understand the basics. So with that, I'll just try to frame my talk. I'll be just introducing the field of spatial data science. I'll talk about what are the core concepts and foundations that you need, and what are the best practices in terms of spatial data science. Not just spatial data science, but any analysis project that you do. What are the best practices? And some case studies that we did. I hope that I'll be trying to run some analysis in front of you just to show how I've done. I didn't put that in the slides, but I'll try to show it how all the workflows work so that you'll get a hang of it. And I just have a couple of slides on challenges and future directions. It's not really much, but I hope that much of our discussions will end up with a lot of questions that you have. And please feel free to stop me whenever you feel like, and I'll be happy to take questions. And if you're shy, I request Dr. Nitin to take note of questions in the chat if somebody is putting in. And maybe I'll stop after a couple of minutes, after 20 minutes, maybe you can just read out if there were any questions, so we can take forward the discussion. So with that, let me introduce you to spatial data science. But before that, we really have to talk about why we are here, right? The public and professionals, and extremely important to talk about the relevance of GIS in public health especially, and it's very important because as of now it's been repeatedly being showcased as a very extremely useful tool to provide a fresh outlook in public health. So also allows me to have. Yeah, I can hear you.
Yeah, the people are saying that the audio is little not clear. So can you maybe keep your mic little clear, your face or something, near your mouth?
Yeah, what I'll do is I'll try to switch over to.
Yes, Hina has raised hand. Hina, the same audio is not clear. Yeah, we're fixing audio.
How about now? Are you able to hear me?
Yeah, I can hear.
Is it better?
Yeah, I think Hina Robinson can tell us.
Yes, it is better compared to.
It's better. Okay. Sorry about that. So yeah, we were talking about what opportunities GIS has for public health, and it can support better planning and decision making, but also there is a convergence of multiple specialities and fields in terms of public health informatics, health and medical geographics, and recently the newer addition is data science. We all know about the John Snow's map, but a couple of centuries before that is a little more relevant depiction of how GIS has been used for public health. So this is a map that has been made of the military quarantine contingent of Naples in the late 17th century, 1690 to 1692. And if you can see in the middle right corner, there is a barricade of posts which depict that the people infected were confined to these regions, and this is a testament to show that the not only the principles of public health and quarantine are being used from back then, but also it's the first depiction of even there is a scale bar and the north arrow and things like that. So this is one of the first maps of public health, if you really want to think about it. But recently there have been a lot of advances in applications in the field of GIS in public health and disease surveillance, environmental health, climate change. In infectious disease models, we have mathematical models, agent-based models. A lot of newer advances have come, and maybe I don't know if we'll have time, but there is a lot of advances again in the field of population genetics, medical imaging, cancer biology. It's really interesting because how you can think that, okay, how can GIS work in cancer biology? But if you think about it, some of the principles and core concepts we use in GIS, like clustering and things, also work in the nanoscale, in the microscopic world as well. So there's been interesting studies that have been published from the Harvard and Cambridge universities talking about how clustering of microenvironments and of the cancer cells and how their trajectories, how they move about in infiltration, and these are captured through again the spatial part of epidemiology. So I would still call it spatial epidemiology, but maybe from a nanoscale. But yeah, we are all. I don't have to explain this map that you have on the right. It's the John Snow's map, but it's a little old in the sense that there is a lot of technical advances, newer methods, advancing technologies that have become quite intuitive and where now mapping is no longer a two-dimensional interface. It's more of an interactive component, and these are the things that are more engaging with the health system and even the public health researchers that allow better decision making, to be frank. Now that we had this previous little talk about why GIS is relevant to public health, but what really is data science and what really is spatial data science that we're talking about? I would not define it because there are contrasting definitions in terms of what the real definition of spatial data science is. Some talk about it as a subset of data science that actually focuses on unique characteristics of spatial data, in the sense that they the traditional GIS was talking about looking at where disease was occurring, and now we are happening to move to understand why is this disease occurring here. So it's moving beyond looking at where towards understanding why the disease is really happening. And there are two stalwarts in the field of spatial data science, Roger Vivant and Edgar Pezilma. They talk about spatial data science, like data science, has cropped up out of need. It arose from a bottom-up approach from many existing scientific disciplines and also industry, and they are now concerned with the application of data science rather than it being a sub-discipline or a subset of something else. It's a discipline that is formed out of necessity. If you think about it, there's a lot of data being generated, there's a lot of travel that is happening, there is a number of things that is happening. But why is it really a new thing? It's not really a new thing, but it's a old thing, but coming out from a bottoms-up kind of an approach. Yeah, how different is it from data science? I would say that sorry.
Yeah, Dr. Arun, sorry to interrupt you.
Yeah.
Yeah. Again, people are saying not clear. So, is it possible for you to close your camera?
Yeah.
See whether it can improve your audio clarity.
Yeah, definitely.
Thank you so much.
Just a minute. Let me try and do that. Yeah, I'll turn off the fan as well. Maybe that is the thing that is disturbing.
Yeah. You can try that.
Is it better now?
Yeah, for me it was very clear, but I think for some people, maybe due to little poor network, it is less. But now you can, I think people are, yeah, you can continue, Doctor. Yeah, thank you.
Yeah. I'm sorry for technical disturbances, but yeah, we were just talking about how different is spatial data science from real data science. But what really is data science? Actually, you should understand that data science is not a separate field in itself. If you look at the purple circle, it talks about domain expertise. It's substantive domain expertise in the sense that you have to have some kind of expertise in your own field to be a data scientist. So if you think that just computer skills and statistics and you're a programmer, you're not really a data scientist. You have to bring in that expertise that you have in your own field. So data science can be spatial data science, it could be environmental data science, it could be climate data science, it could be financial data science, it could be computational neurological data scientist. There are n number of subspecialties within data. By definition, data science means you need to have expertise in some branch. So for us, it's public health, right? We are all public health professionals, so we are bringing in the public health expertise here. So, but what expertise do you need in terms of being a data scientist? There is n number of things that you really have to have. You're not just a programmer, you're also something that you have some intuitive business sense. You know how to work with data. You know how to work with large databases, data systems. You know how to use the cutting edge predictive models and things like that. But now comes the spatial aspect, in the sense that you have these three previous things. You have your domain expertise, you have your computer programming skills, you have your statistical knowledge, but now you have to have substantial knowledge on the spatial sciences as well. And all of this is sciences. Later on you'll see have a small quote from J.K. Leek, who is heading the John Hopkins data science lab, and he talks about the keyword in data science is not data but science. We'll look at that later on, but you really have to understand that each of this is a subspecialty in itself, and each of the converging areas that we're talking about is really to be a real spatial data science person, you need to have expertise in all these domains, but you don't have to be an expert in all. You need to have some kind of expertise. You need not be an expert, because much of the times you will be working in a multidisciplinary field or a team, right? You will have a GIS programmer, you will have a statistician, you will have a epidemiologist, you will have a computer programmer in your core team, so that you can really draw from the expertise from these multiple subspecialties. But you need to understand the way they speak. So you need to understand and converse in their language, to be frank. And earlier, maths was the lingua franca when I teached it, at least when I was studying. But now, computer programming is a language that not only interfaces with humans but also computers. So that is the new lingua franca for me. And now, why spatial data science for public health? I feel that we are all familiar with this, agent-host environment, the real epidemiological triad or tetrad or whatever. And this is I'm not saying there's something wrong with this, approach, but we have to understand that world is moving forward, so we should also move from our regressive thinking, and it's no longer a two-dimensional triangle that we have to think about, and it's not vector. It's not a pyramid as well. It's not a three-dimensional pyramid, but you have to think of it as a network in the sense that now think about this as agent-host environment, in the sense that the environment is not just a single environment. It's the temperature, it's the precipitation, it's your built up index, it's your how you're using your land, and you have and all these environmental factors depend on the distributions of populations in these separate areas. And when I say distribution of populations, I don't just mean those of humans, but also of vectors or any agents that we're talking about. And now that we have this, there are also some kind of aspects that really need to, just because you have a vector and you have a host and you have an environment, does not mean that a disease will happen, right? So some areas might have higher risk, some areas might have lower risk. And it's not only that, just because a case is being reported in a area does not mean that there is no case not being reported from an area does not mean that there is no case in that area, in the sense that the health system's capability of picking up cases is also important. And all that, yeah, when we study public health or community medicine, we really think about all of them. We are taught all of these, but we really are not equipped with the tools when we are out in the real world. After our community medicine, MD or whatever, when we go out in the real world, we just nod our heads and think about it, but we don't really have the tools and expertise to do things. So that is where I appreciate Dr. Nitin's effort to have this kind of engagement and gathering, so that we update ourselves with newer techniques. Okay, now when I say what are the newer techniques, and this is an example of an agent-based model. It's done in Julia, but the green cases are actually, it's a simulated outbreak of because every green dot meets a black dot who is non-infected, and they're walking in the path that is directed. It's not that all spatial areas are having the equal risk of people moving, right? So there are areas where there is higher risk, there are areas where there are lower risk, and there are predetermined areas where people walk by, and there is a probability of not 100% probability. Everybody you meet, you will not give the disease. Maybe based on these hyperparameters, you build a model and see, okay, now let me run 100 simulations or 2000 simulations or whatever, and then see what really happens. And this is something called as a synthetic population in the sense, and these are newer kind of advances that are happening in the field of spatial data science. But we are still not yet there. In the sense, these are all newer techniques, newer methodologies that are just coming out, maybe a couple of years back or a couple of months back, to be frank. But we do have access to these techniques and methodologies now, but there are certain limitations that we do have. We'll be talking about them later on as well. But this is what I wanted to talk about, in the sense that we have a wealth of spatial data. 70% of all data that is being generated has spatial attributes, in the sense that every photo that you take, every image that you send, it's all mobile generated. Everything has a geotag, geolocation, and even health data that we are collecting today through the routine health system. We are collecting it much faster than we can swallow, in the sense. It's not just about swallowing, it's also about looking at it, analyzing it, discussing it, and also drawing inferences from it, and also working on it, whatever the data is speaking. We still don't have the expertise. We still don't have, not just, I'm not talking about the capability of the doctors and staff, but I'm also talking about the infrastructural needs that we have. as a country, we really don't have much expertise in this area, and we're still learning. And now, now that I think I've made my case for the need for this field, I'll also be talking about some foundational concepts in this field, and not just in spatial data science, but also in GIS in general. One of the core concepts that is related to GIS and any kind of spatial analysis, including spatial epidemiology, is the Tobler's law of geography, or the first law of geography. Even before, I mean, I know that Tobler has been, conferred with this title of father of geography, and he is the first law and all of that. But if you remember, Dr. R.A. Fisher also has talked about similar kind of law, which talks about everything is related to everything else. But things that are near are more related than those that are far away. That's the, for example, I think if you think about it, things that are near are more related to each other than things that are far away, right? If I'm more similar to my brother than somebody else who is living in Ukraine. So things that are, I mean, when I say things, it's not just things, it's humans. And especially, for example, if there is rain falling here, just 2 meters or 10 meters or 1 kilometer away from me, there also maybe it might be raining, rather than somewhere around 500 kilometers, it might or might not rain, right? So it's not just about humans, but also about the environment, about many things actually. So another concept, I hope you're all clear with the first law of geography. I see a couple of hands raised, but just bear with me. Maybe in a few minutes we'll talk about it later on. Now let's come to this. Just building on the first law of Tobler's first law of geography, the concept of spatial dependence. It's nothing. If you just think about what is dependent, the propensity of nearby locations to influence each other and to possess similar attributes, right? I might influence the person near me more than I can influence somebody else far away, right? So I have spatial dependence to the people around me rather than the people that are far away from me. Okay. So this is a naturally occurring phenomenon, right? Temperature, people, I mean, why is it colder in Himalayas? And why is it a little more colder in Nepal? And it's hotter here because of the, distribution of weather, and that is not random, right? Even population density, why are cities around New Delhi and Mumbai and all the suburbs, they are more dense than far away areas? Because our assumption is that for any kind of statistical test, right, one of the main assumptions is that everything is not related, there is no dependence, or we call it they are independent of each other. All variables need to be independent. But through first law of geography, through Tobler's law, it is quite clear that it is a paradox because near things are related to each other. So there is never any spatial, there is never any independence. But we can look for this kind of a phenomenon, and it can be measured by certain indices called spatial autocorrelation. Okay. Just have a look at this figure. The central, checkered spot, that whatever you think about, is they're regularly dispersed, they're equally distant with each other. Whereas the far left, which is having certain clusters of or a correlation of these dots, and that you would call it a clustering, or non-regularly, non-random pattern. And when things are not, there is no real pattern that is visible, not just visible, but also statistically it's not there, then we call it a random thing. So complete spatial randomness is a null hypothesis that we think of, right? If we are able to prove that there is no complete spatial randomness, then we would say that there is some kind of pattern, right? Okay, yeah. Now we'll build on to these indices of spatial autocorrelation, but just in adding on to it, the term spatial association, spatial dependence, they almost always reflect the concept of spatial autocorrelation. And just like any kind of correlation, you know that there is a positive correlation, there is a negative correlation, and there is no correlation, right? So when I say no correlation, that means things are random. Okay, things are not occurring. But when I say negative spatial autocorrelation, that means when you normalize the variance, they are equally dispersed. Okay, the dispersion among these variables, these data points is constant, and it can be seen from the central part, like whatever you see that there is no clustering, there is complete uniform pattern, that is something called as a negative correlation. In the far left is the positive correlation, and there is a clustering of cases, or of these blue squares, they're all in one corner. So I hope that you understood the concept of spatial autocorrelation. We'll come back to this again, but this is one of the core concepts, because if you understand Tobler's first law, that talks about near things are always more related to each other than the far away things. That builds on to the concept of complete spatial randomness. And complete spatial randomness is something that we try to look for, and in order to look for that, we came up with this indices of spatial autocorrelation and spatial association, spatial dependence. These are similar words that are used in the same context, and we come up with indicators that look for this, measure this spatial autocorrelation. So there are any number of measures that we really think about. We can talk about covariance functions, variograms. I'm not going to go into the details of any of this because I know that this is a introductory session, but maybe in the future somebody can take these up and we can discuss and do all of that. But just understand that there are something called as a global measure and a local measure as well. Okay, global measure talks about from the whole of the overall picture, is there any kind of spatial association or not? Spatial dependence or autocorrelation. There are three different, not just three, there are more, but the commonly used three ones are, in fact, not also three, only Moran's I is most commonly used. But yeah, there are places where you use general G statistics and Gay series also, Gay index as well. And there is one other concept of local indicators of spatial association, is that from an overall picture, is there any spatial autocorrelation or not? If yes, then Moran's index or G statistic or Gary C will be a significant way to, we'll be able to pick it up. But the next question is, okay, if there is a spatial autocorrelation overall, where is it? Okay, where are the places where there is, for a lack of a better word, it's called hotspots, right? So for hotspots, it's not a lack of a better word, it is the correct word to use. So all these hotspot analysis that we do, that is nothing but your Moran's, local Moran's or Lisa or Gettys or GA star. Local Moran's is, again, it gives in terms of your Z scores and it gives 5 different levels or 7 different levels of categories. But if you really want to break it down into whether it is a hot spot or cold spot, I'm not interested in anything else, then you go for something called as get is or GI star. Okay. Now that you have this, we're only looking at the spatial patterns, but now we are also adding on one more component of the space-time correlation, or space-time is 2 different entities, because things can happen sequentially in the same area, right? And there is not only a spatial factor that you need to take into account, but also a temporal factor, right? So for this, there are additional measures of spatial dependence in the sense that it is not only related in space, but is it also related in time? So we go for this bivariate Moran's I statistic for space-time correlation, or you also go for this differential Moran's I. But recently, a newer method has been developed. It's called emerging hotspot analysis, and it adds on to the previous way of LISA, or local indicators of spatial association, telling whether it's a hotspot or cold spot. And you look at it temporally in the sense that, was this a hotspot last year also, next year also, previous than that, last January, February, March, April, May. Okay, if it's a hotspot all these times, now let me categorically give you a definition that, okay, if you have been a hotspot for this long, I'll call you a persistent hotspot. Okay. Or if you have been a cold spot for all this while, out of 7 months, if you're a cold spot for the last 5 months, then you can be termed as a persistent cold spot. If you have been moving from cold and hot, then you're an oscillating hot spot, or oscillating cold spot. And you can have you were a cold spot earlier, and now you're turning out to be a hot spot, and that is where you pick it up and call it an emerging hotspot. I hope I'm making myself clear. It's difficult to understand the statistics and mathematics behind it in the first go, and I'm purposefully ensured that I'm not putting any formulas in the slides. But just to visually depict it, this is what I mean to say. When Moran's I is greater than the expected I, then you would tend to say that it is clustered. If Moran's I is less than the expected I statistic, then you would tend to say that it is dispersed, or it is negatively autocorrelated. And if it's equal to the I, then it would be 0. It would be random. So usually what happens is this variance statistic, which is I, is normalized to be between 1 and -1. So if it is 1, that indicates clustering. If it is -1, it indicates dispersion. And if it is 0, it means that there is nothing, okay, or random. I hope I'm making myself clear. Now I have a very busy figure here, which talks about a method that we usually do is it's called the LISA scatter plot. Okay, so scatter plot is the points are usually plotted against the x and y axis based on their lags, x and the lag of x, and you can fall in one of the 4 quadrants, right? You're either high, you're high-low, you're low-high, and you're a low-low. What that means is that if you look at this, I don't know if I have a pointer. Okay, are you able to see my pointer? Okay, so this is a point that is falling in the high cluster, high category. What this really means is that it is a high cluster, or it is an area, not a cluster. It's an area which is high, which has high values. It could be temperature, it could be it could be people with high proportions of BP. It could be people with higher prevalence, So anemia or whatever, it could be anything that you can think of. The value, whatever you're measuring, it is surrounded by areas or people who also have high values. Okay, I hope I'm making myself clear. So high means you not only you are having high, but you're also surrounded by people who are high or areas who are high. And now this low high cluster or low high point means that you're low, but you're surrounded by people who are high. Okay. And again, low means you are low, but you're also surrounded by people who are low. That's what it really means. And uh, this is quite a reductionist view, very bare minimum things. But we need to understand that here only 6 points are there. But just like any statistical this thing, they say that you need to have at least 30 data points to actually credibly comment on something like this. Okay. Okay. There's a very another complicated concept called coordinate reference system and map projections, and it's really first time when I heard this or read this, I was like, what the hell is this? I don't really understand now. This is not really of any use to me. But I started looking at it, and as time progressed, I really understood that these are one of the things that are really important, especially when you're doing any kind of spatial manipulation, data manipulation later on. Basically, what this means is there is a projection system and there is a CRS. And the projection system is trying to transform the Earth from a spherical shape to a cylindrical shape. Okay. So if you look at the A row, it's a cylindrical shape, and it's like a paper cone, paper cylinder, and you're cutting it and you're pasting it as a flat on a flat surface. And the B is that you're looking at it from a conical perspective. So these are called conical projections, and then you open again and make it as a flat surface. And then you have this planar projections, which look at it from the top view, the sagittal kind of view, not sagittal, the top planar view. And you again look at it and then paste it on a 2D surface. Now, what is the relevance of each of this, and why is one important than the other? I also used to feel that, but slowly I realized that depending on what work you're doing, what kind of analysis you're doing, and what is the area that you're working with, it's really important that you decide on what map projections and coordinate reference systems you use, because some of this will be in degree decimals, in radians. Sometimes you want it in meters, sometimes you want it in kilometers and things like that. But most of the time, it's usually based on the available data that you have. But luckily, through these softwares now, we can convert one reference system into another as well. Just to give you a perspective, why is CRS really important is that we all look at Earth and think of it like a sphere, but really it's not. It's not an ellipsoid, it's not a spheroid, but in truth, it is a geoid, in the sense that from point A to point B, the distance will not be the same at every location of Earth, in the sense that when you use when angular relationships are important, you use this Mercator projection system, but the relationships are really distorted. But when you want to look for this proportional relationships to be preserved, you go for this small v equal area cylindrical projection system. That means that every square has equal area in its this thing. And this a planar system, like this is also an equidistant system, like from point A to point B is the equal distance, and that's how it is measured. And there are a number of, this is a compromise kind of a situation where Robinson projection has a compromise over angular relationships as well. And if you look at the WHO nation's logo, it uses the azimuthal equidistant projection as that is the top-down kind of thing that we looked at. And this is how if you really want to ingrain it in your brain on what really is this CRS, then you can think of this view in the sense your head, if you look at it, what kind of distortions can happen. The first one is I think it's a the top bottom right one is a planar system, and the above one is a cylindrical system. The left bottom is a stereoptic projection system. I'm also confused with things, but there is one really interesting tool which is called the truesize.com, which really helps us to view this much better, in the sense that okay, are you able to see? Yeah. Okay. I'll just ask you a question. If you want to respond, you can respond. By looking at the size of India, and can you compare it with Greenland, which one is bigger in area?
Greenland.
So India is actually bigger than Greenland.
Yeah, Greenland is bigger, no?
But no, in actuality, India is bigger because there is a special.
Yeah, but in this map, Greenland
yeah,
looks
because the
bigger
map has difficulty.
So now if I take this and put India beside Greenland, look what happens. What is bigger?
India is bigger.
India. So this is something that you need to keep in mind, right? For example, if you are thinking that from Delhi to Kerala or Trivandrum, where I am, the distance is the same, and you're thinking, oh, this will take a lot of time to go, and you see, it's exactly much farther, isn't it? So you can bring it down here. You can see that, okay, in fact, Greenland is smaller. Okay. Again, the same thing with Canada, because you look at it as a spheroid, right? In the sense that these corner areas, and they are actually made it into a bigger this thing. If you look at Russia, if you bring it, it's relatively smaller, isn't it? Okay. I know this was surprising for me as well when I initially looked at it, but yeah, maybe later on you can play around. Okay, I'll move forward now. Okay, before I talk about, now that we talked about the core concepts of GIS, okay, now I'd like to take a break and ask a few questions that you had. Some people had raised their hands. So if, or Dr. Nitin, would you like to moderate some questions now?
Yeah, thank you so much, Dr. Arun, for that wonderful insight into what is spatial epidemiology. So if anyone has any question, somebody has question about Google form. Yes, post test is coming up. Okay, the moment Dr. Arun Mitra finishes his session, then we will have post test quiz. So you can try your luck. Yes. Apart from that, any other you have?
Yes, sir.
Karthik, yes.
Sir, for this autocorrelation thing which you told, we are. Is it a statistical technique which we are measuring with Morans index?
Basically, the concept of autocorrelation means that near things are related to each other than the farther things, and this does not hold true only for spatial data, but also the temporal data, in the sense that you are taking somebody's you have a sensor that is measuring somebody's blood pressure or blood glucose. Now you have the CGMS values, right? If somebody is having dinner at 2 o'clock, sorry, lunch at 2 o'clock, their blood sugar values will peak around 330, somewhere like that, right? So you can expect the value which is at 15 minutes before 3:30 or 15 minutes after 3:30. It will definitely be similar to than it was at 2 o'clock. You get my point?
Yes.
So this spatial or temporal dependence has to be accounted for when you're doing any kind of statistical test, because the conventional statistical tests take an assumption that things are not really, one of the major assumptions is that every variable is independent of each other, isn't it? But in fact, it is not, especially when you're actually looking at the spatial aspect. Just because you take a latitude, longitude into your data and you do an analysis, it will not work that way, because these latitude longitudes are actually pairs of latitude longitudes, like you looked at the CRS, isn't it? So that 1 degree difference in India might be 20 degrees difference in Greenland. Okay, so we really need to take those things into account when you're actually looking at any kind of statistical tests. But it is a good practice to look for this spatial autocorrelation and test for it. And based on what you want to do, there are additional methodologies that you can go for, in the sense that if you're looking for clustering, you can use there are n number of algorithms that go for use for clustering, but based on your kind of data, you can actually take a decision on what method might be more appropriate. I'll not be talking much into the the technical things, because I wanted it to be a little overview of the whole thing, rather than going into nitty-gritties. I hope that answers your question.
Yes, sir. Thank you, sir.
Okay.
Yeah. Thank you so much, Arun, and thank you so much, Karthik, for the question. And we have one question by Robinson. Could you please repeat equidistant UNICEF thing? I think the question is not clear. So Dr. Robinson, Thomas can open your mic and you can ask questions.
Okay, I'll just show you this, what I was talking about, in the sense that we now know that there are n number of projections that you can do. Okay, one could be based on each. Okay, I think there is a thumbs up. I think after that interactive map, I think you realized what it could be, isn't it? Okay, I'll just continue from here. If you have any questions, we can take it in the end. Is that okay?
Yeah.
Yeah.
Yes, we can have more questions at the end. Okay. Thank you so much.
Yeah. Okay, great. So now, yeah, I was talking about this Jeff Leake, and he was the co-founder of this Data Science lab at Johns Hopkins, and he talked about data science being used very loosely, the word, and he talked about how the keyword in data science is not really data, but it is the science. Because if you remember the Venn diagram, if you really have to be a core data scientist, you have to have some kind of domain expertise, and it itself is a science. And just because you're doing some statistics with some programming, copy pasting some code that you got from the internet, and you're running it, and that does not really work that way. But nowadays people are realizing, even big journals are realizing, that as a methodological approach, data science has an edge over other traditional approaches, because it not only looks at the data holistically, but also it allows you to verify and be open, in the sense that if I do some analysis on Excel and I will write a paper, and it might get published, but if somebody else wants to run the same, verify what you have done, you must have written your methodology, the documentation very clearly, or you must provide your own data, which version of Excel you used, and what formulas, what, and all of that has to be provided to the end user, who is an academic researcher, or MD student who is looking for what could be the prospective thesis ideas and things like that. But With all that said and done, there is something called as a reproducibility spectrum in terms of academic research. Okay, the gold standard, and there is a traditional publication only kind of a standard. So no longer journals accept only your publication. They always and always ask for code. Along with the code, if you are able to give them the data, real data, and also just giving them the code and data is not enough. They should be able to run the code with the data in their own system and should be able to do that. Okay, only then it is called a gold standard reproducible research. And this is an accepted term. Academically, it's all good journals ask for this full replication model. But provided if you're especially doing some kind of GIS analysis, yeah, you will be able to give them your data, you will be able to give them, but yeah, I know that ethically it might not be possible to give the lat and long of all cases that you have and all of that for security reasons and ethical reasons. But provided if you are able to do that, all anonymization, all methods of masking have been applied and things. Even then, if you're doing it in some software like ArcGIS or something, you will not be able to give them the software, right? Because he has to purchase the ArcGIS. Or even, for example, if you're doing a non-spatial analysis, if you are, that holds true for this SPSS in Stata, somebody has to have the license for it, no? So that is why the academic community is moving away from the proprietary softwares to this open source solutions like R, Python, Julia, whatever the solutions are. Okay? Even QGIS is open because it's free of cost. But the problem with QGIS is that many of the things is that you have to do it manually. And documenting that manual process is really difficult. Okay. Now that I've made a case for data science as a novel methodological approach, I'll be, yeah, this is one of the, 4 key elements of, reproducible research. You need to have data that is documented correctly. The publication of the data has to be precise, proper, all errors, outliers, everything needs to be looked at. Also, the code that is being used for processing this data has to be meticulous and should be provided on the open domain. And also, the output publication should also be, for example, if I made a couple of maps, right? If somebody wants to replicate those maps, he or she should be able to replicate them, provided you have given all the data. So the output publication also has to be provided. And now we'll talk about a little about what are the tools for spatial data science. There are a number of tools. There are GIS related tools, purely data science related tools, and there are spatial data science related tools as well. Considering all of that, I've been working in the first map that I made was around 8-9 years ago. And I don't know how, but somehow I made it in R and Stata. But later on, at that time, it was very, very, very difficult to really get hold of these spatial files. How to do it, we did not know. A lot of, and there was no expertise with us also when we are actually working in this field. So a lot of documentation was not there. So it was mostly a hit and trial and seeing what works, what does not work. And we had to write like 200 lines of code for making a map and all of that. But as time progressed, a lot of tools have come up, and a lot of problems that I faced have also been faced by thousands and not tens of thousands of people across the world. And they came up because that is one of the benefits of this, what do you call it, the aspect of open source research, because a lot of the support that you get is from the community. And one wonderful thing is that our though for purely data science work, I would say that yeah, many people will go for using Python because much of the people who are doing data science are computer programmers and machine learning engineers and IT people, web developers and things like that. For them, for doing a number of things, maybe Python will be easy for them. But if you are a public health researcher, R is the best tool. And not just if you're a public health researcher, but also if you're a spatial data science enthusiast, R is the best tool because R is specialized for statistics and for handling geospatial data. So there are a number of, there is a very nice integration with Google Earth Engine. There is interactive plots visualization, and number of things. I'll show you a couple of those to you now if possible. But this QGIS is one other open source solution for people who are not much into programming and coding and things like that. Yeah, I was talking about the R analysis ecosystem. I'll just I was just talking about this SF package. It's very useful in making maps. This is a very this is a link of CRAN. CRAN stands for Comprehensive R Archive Network. And if you just type CRAN analysis of spatial data, again, this is again from Roger Bivand, who is, I think, still in Norway. But yeah, this is quite current. So it's always updated. It's been updated, I think, 2-3 weeks ago. This includes all the classes of spatial data. It includes what are all the packages: SF package, stars, space-time package, SP, SPATStat is the for analysis of point patterns from SF and star. You have raster data packages. You have not only for this, but you also can read multiple data formats. So any proprietary data format also, proprietary data format is data that is coming from ArcGIS or like people might be using SPSS. SPSS data can also be used in R. However, R data cannot be used in SPSS. So this is cross-platform support. Not only that, you can Google Earth Engines, RGE packages here. You have n number of census data, census bureau data. You have satellite imagery data. You have packages that talk about how to calculate distances and routes. You have data cleaning, processing, sampling, visualization, and number of things. Maybe later on, there's a huge number of lists that you can go for, but I will not waste more time here. Maybe you can just look at it later on. And yeah, I was mentioning that when I was doing my initial steps, taking my initial steps into spatial epidemiology, I did not have much help. But now there is a wealth of resource material available online. There are more than 30-40 books which are free online. You can just Google it and you can just work on it. Everything is meticulously drafted, crafted, and curated for people like us and who have very short attention spans. And R is also very useful in the sense that it can very seamlessly handle both vector and raster data, and it can do interactive visualization, and you can. It is an end-to-end solution in the sense that you can just take the data in and publish a report with the map, with tables, with all analysis from R itself. You don't have to go to your Word and write the document. You don't have to go to PowerPoint and make your graphs or nothing like that. And yeah, you can also develop dashboards and do all these things. And I was just talking about this SF package. It's very simple to install these packages. You just write one line of code and it will install things for you. It's a simple features. SF stands for simple features. Simple features is a very strong implementation that is again, spearheaded by a lot of stalwarts in the field of GIS and spatial data. It incorporates all the new spatial data class formats. Also, it has functions for reading and writing data. I'll show you a lot of methods. It is any number of methods that you can do with spatial geometries. It's just like a table, but you can just add the spatial attribute of each of that row. For example, if you're thinking of I'm coming from Kerala, so I've been working here for long. So I'll just take one example of Kerala. Kerala is 14 districts, and if you have information of these 14 districts, something. So imagine that you take one district and you stick in the last column, right? You're just taking a glue or some sellotape and sticking. Okay, this is the Trivandrum district spatial thing. You take this. So that's the way it looks like. I'll just show you if possible. So there are a number of geometry types, but primitively, it is a industry standard to talk about 7. More than 7 we usually don't use, but yeah, there are 3-dimensional geometries and geometric collections and things like that. Also, like multi-line string, there is a line string. This is called a line string. More than 2 line strings is more than 1 line string is a multi-line string. It's a single point. 2 points are there, so it's a multi-point. The point, line string, polygon, multi-polygon. You can have collection of all of these as well, which is geometry collection. So it's very easy to handle. Like you have a spatial data with some roads, some cases, some area polygon of the district. You also have a river. All of that could be into one single object that is an SF object. I'll just loading an SF package is very easy. I'm just taking one example. I have taken one spatial file. I have a folder in my directory which is called Kerala Population Centers. So this Kerala Population Centers has the spatial files, right? So .shp. See, this is one key format that you need to understand, that .shp is a very important spatial file format. But if you just give somebody .shp, it won't work. Okay. The reason is it needs 3 other formats to work. It is a proprietary ESRI format, which is made by the ArcGIS ESRI ISRI industry. Yeah, I'm very thankful for them. But one of the major problems with that is that you need to have all these supporting files, right? So sometimes when you're attaching shapefile, you just tend to send this, and all these 3 are like lying in your inbox only. They don't go, and the person there cannot open this file again. But yeah, it's very easy. Just 2 lines of code to load the data. This is, I mean, in fact, it's only 1 line. I'm just saying that, okay, this SHP is in this area. Here, it is here. And I'm calling it a shapefile. And I'm saying ST. ST comes from the package SF. It's a spatial table. I'm saying it's a spatial table, and you read it. And I'm saying I'm reading it as a object in R called KL Population Centers. So if you look at the aspects, it's saying that I'm reading this layer from the data source that you have given. I'm using the ISRI shapefile. It understands what shapefile it is. And it says that, yeah, you have 170 features of 14 fields. It's a point geometry, and yeah, the bounding box is this, and whatever. This is the geodetic CRS WGS84. I'm not going to the CRS because I have eaten your brains enough today. But yeah, that's an important topic of that you really need to understand. And yeah, this is how when I type SF, when I type KL Population Centers, it says, yeah, it's a simple feature collection of these many features, these many fields. It's a district. One is district 1, district name. It's Palakkad, Ernakulam. So a number of things. It's saying that, okay, this is the population of that year. This is the lat and long of the center, and it's giving me the points. And now if I try to plot it, it's very easy to plot. So I'm just taking this object, which I know is an SF object, and I know people are not familiar with R or the spatial way of plotting things, but yeah, ggplot, just 2 lines of code, I'm able to prepare a plot for you on R. Yeah, Robinson's, I think it has to do with the data. I have cleaned it, but yeah, these are some of the problems when you're converting. No, it's nothing to do with R. It is the format problem from where I got the data from directly. And just with one argument saying aesthetic or AES is color is district, color it by district, and just coloring it by district. It's very simple. And yeah, this is how we plot things in R. The concept of the SF package is that it works both with vector data and raster data. You can read the data and write the data using these functions, read and write. There is no very difficult, rocket science kind of this thing. Everything has a prefix of st underscore, and it is read write. If you want to get information of the CRS, you'll say st underscore CRS. If you want to get the information of the geometry, you'll say st underscore geometry. If you want to transform the data from something to something, you just use these verbs. And if you want to find out the distance, area, anything you want to do, you just use the methods. I'll just show you the methods as well. There are a number of support. I don't want to show this slide as well. I don't know how it came. But yeah, these are the different methods I was talking about, in the sense that you can aggregate data. For every SF object, you can aggregate data, you can join, anti-join, you can arrange, you can convert it into a data frame. Data frame means a table. You can drop all NAs, you can filter it, you can fully join it, you can gather it, you can group it, anything you can think of. Okay, you can pivot longer, pivot wider, you can rename it, you can do row-wise this thing, you can separate it as things. There are SF method, ST methods as well. You can crop it, you can cast it. You can get the coordinates, you can get the CRS, you can find out if you have 2 different SF objects and you want to see which areas are overlapping, you look for ST intersection. You can merge them, you can union them, you can simplify them, you can do n number of things. Okay. This is where I was talking about interactive aspects of this thing. For example, for each data point, I'm now able to just click on it and all the attribute is coming. Now the population is this month, that long, it's an SF point. This is Sultan Bateri from Wayanad district. Yeah, and I can zoom, or I can also change the background of these. I can go for any kind of Esri world imagery. I can change this as well. But yeah, I hope that I tried to make a point saying that all of this is possible within one framework. And interestingly, I'm putting it in my slides as well. Yeah. And this is made possible by one extension, leaflet, just like we said in library SF, we say library leaflet. Then yeah, it's lightweight interactive class platform. Yeah, there's a lot of help that you can look for. Now coming to the best practices. I know that it's getting late. I know that we have 10 more minutes, but yeah, I'll try to rush through. If you guys want another more time, we can just talk about that as well. Yeah, there are some best practices, data related, analysis related. Exploratory data analysis is the first step that you do in any kind of analysis. And what is EDA? EDA is mostly a philosophy of data analysis, but it's like looking at the data without any kind of preconceived notions. And you can John Tukey, he was talking about EDA as something that is a detective work, and it's a numerical detective work, or it's a graphical detective work. You need to think of it as you trying to explore the data and ask it questions. So questions are very key here, in the sense that the easiest way to do exploratory data analysis is to use questions as your tool, okay, to guide your investigation, to guide your detective work. So EDA is an important part of analysis, even if the questions are already known, in the sense that you should not take it uh, as something that is mundane, but asking the right questions is key. But it's also important that in order to ask the right questions or quality questions, you need to generate a large number of questions as well, because you don't know what question is going to lead to what answer, isn't it? Even though you know the answer, sometimes it might surprise you. So usually what happens is that you have a question in mind, and in order to answer that question, it takes a lot of time. There's a lot of latency, right? You really have to think about how to pose that question, where to load the data and analyze it, and maybe once you do all that posing question, the answer might not be. And through that, while you're answering that question, some other question might come up in your mind, and you might lose track and all of that. So if there is a way to efficiently ask these questions and decrease the latency of answering these questions, that would be phenomenal. And that is what data science helps you to do, in the sense that it helps you to ask questions quickly, get answers quickly, because everything is just copy pasting and reframing it. Otherwise, if you have to do it manually, if you want to do the analysis manually, it will take you any number of times. You might make a mistake. Instead of mean, you might calculate a median, and things might go wrong, right? So you're also prone to errors when you are doing these kind of tasks. So there are 4 or 6 W's in spatial EDA. We call it exploratory spatial data analysis, ESDA, and that's not a made-up term. It's an actual accepted word. The first 4 we know, right? We want what is the problem, where is the problem, when did the problem occur, and who are the people where the problem is. But what we're trying to do is to add those last 2 questions. I know because it's from moving from where to understanding why, right? And sometimes understanding why, we should also know how, isn't it? So that's the 6 W's of spatial data analysis, or exploratory spatial data analysis. And there is a process to it, but it's an iterative process. You import the data, you clean the data, tidy the data, you transform it, you visualize it, you model it. And this whole cycle of transform, visualize, model will take a lot, iterative process. It will take multiple cycles, and then you communicate the result findings. So there are multiple steps for any good data analysis project. It asks, and this is again from one of the best practices document of ESRI. They also talk about ask questions first, prepare the data, analyze and model it, interpret the results, repeat or modify, present the results. So it's like a iterative process where you do it again and again. And there are any number of things that we really have to talk about in terms of best practices, which is again talking about the cartographic principles, in the sense that because cartography means map making, and it's very difficult to make a map, a good map, because it requires for you to have visual contrast. It needs to be legible. It needs to have good ground orientation. This is what I mean by visual contrast. On the left it is a good contrast, on the right it is poor. But in the second row, the left is poor and right is good, because you're not able to differentiate the foreground from the background, which is water, which is this you're not able to see. And one other example is the legibility. You're not able to really appreciate which is a bigger point and which is a smaller point in the first row. In the second row, the text is not really visible. And then, if you have to make a map, and making a map right in the first try will take a lot of time. Okay, so it's really important for you to make it, in such a way that you, are able to reproduce it very quickly. So what better than, usually you copy paste the code and do it, right? A number of things. I have a number of examples, but in the interest of time, I'll just skip all of them. But what about public health, right? So based on this cartographic society, GWSA, or the working group of the whatever, CDC then took up these guidelines, the 5 guidelines we talked about, and gave some pointers on, okay, if you are making a map for public health purposes, what are the most important aspects, right? And some of these are in here. They talk about having a proper title. They're simple things which we usually often miss, and we really don't take care to, because map has to be self-explanatory. If you look at the first map that I showed of Spain, it is a hand-drawn map, but all of the details were there. But since those days, there is only specialized cartographers who can do that kind of an exercise. Not everybody used to make a map. Actually, in fact, John Snow's map, John Snow had to make, I think, more than 35 versions of the map. And even the map that has become popular also had 2 errors. Two deaths were missing in the map. So he had to come up and give another version of the map, but that never came to be. Somebody else actually found out that there was an error. Anyway, so you need to also talk about where this data is coming from where to where you have taken the data from, what is the projection. That is really important. Like WGS 84, because if you don't show it's always not possible to show the full picture, right? Just like the different, orientations, and if you're using, the true size, it also changes. So it's also important on what projection and scale the map is drawn, because much of the times it also needs to include the inset map as well. Yeah, I know that we are missing on time, but for the case studies, what I thought was sorry. Just 1 second, please. Yeah, are my slides visible?
Yes.
Yes. 1 second. So yeah, I'll skip all these. So one case study what I wanted to talk about today was a public health problem, rising cesarean sections in India. And there are a lot of evidence talking about the misuse of this wonderful technology of cesarean sections, but it's not really clear on where and what is the problem and by how much. So what we thought was we could bring in some geospatial methodology to uncover these hidden inequities in maternal health care and generate evidence and aid policy decisions. The idea is to look at the patterns of cesarean section in the state and district level and to investigate clustering across cesarean sections. And for this, we used 2 data sets. One is in fact 3, the NFHS 4, NFHS 5, and also we try to collaborate it with the HMIS information. And the NFHS 4 and NFHS 3 are, sorry, 4 and 5 are actually given as PDF documents, and the data is not in spatial format, and it's not even an Excel file, it's PDF format. And there are more than 100 indicators of maternal and child health, and much of these indicators are written in a tabular format, and it's very difficult to extract that data. But also this HMIS information systems data is a longitudinal facility level data from 2011 to 2019. So this is talking about the monthly reports of cesarean section. So the resolution, when I say resolution, spatially there is a resolution, but there is something called as a temporal resolution as well, in the sense that the data sets in the first case, NFHS, are actually survey-based data, which are collected at one point, you know, and in fact 2 points for NFHS 4 and NFHS 5. Whereas for the HMI system, it is monthly reports for almost 10 years. And these data are Excel and CSV formats. And if you are thinking about analyzing data from these sources manually, it will take you years to actually come up with a real interface or real corpus of data. So that is why we have chosen to go for a data science approach. And there are 3 steps that what we did. Even downloading this data, see, there are 746 districts in India, and downloading 746 into 2, because for 2 years, for 2 NFHS, we are trying to download the fact sheets. Doing that manually also will take 1 week of my time. So what I had to do was I had to write an algorithm which goes to the website, searches for the year, clicks on that PDF, right clicks it, and also saves it in the right folder, right format, in the district, sorry, in the state. Create a state folder and name the district, name the PDF also in a way that I want. So web scraping is also a skill that a data scientist need to have. And now that these PDFs are there, we have to convert them into Excel or CSV sheets, in the sense that we had to extract the relevant, because they're all PDFs which are like 6 pages, and single tables are actually across multiple pages, and it's very difficult for a person who is copy pasting and taking that data, the right data, and typing it somewhere. It will be prone to any number of errors. So again, we had to take a call, and we had to write algorithms that also can fetch the data from these PDFs and convert them into Excel files. And then we need to clean the data. You need to wrangle the data. You need to link the data. There are n number of things, because NFHS 3, 4, and 5, sorry, 4 and 5 had to be spatially geocoded, geolinked with the shapefile of India, in the sense that NFHS 4 had a different number of districts as compared to NFHS 5. And also the spatial file that we had different number of districts. So we had to also modify the shape file. And also we had to, and then we had to finally create a unifying database of all the data. We just wanted to find out if this is possible to do with, ArcGIS as well. So what we did was, though it is 100% possible to do it in R, we also wanted to show that R is powerful enough to work with proprietary softwares. And so we tried to integrate the ArcGIS package for R, which is ArcGIS binding, and bring in these newer methodologies. Even though newer methodologies are available, but we wanted to show that we can integrate both these things. So just to show you NFHS 3, 4, and 5, there is a subtle increase, not a subtle increase, but there is a significant increase in cesarean sections by time. But also, if you look at the right side, there's a line graph which is showing that the private hospitals are higher as compared to the public hospitals. But if you look at NFHS 4 and 5, within the public hospitals, the increase looks a little uniform, whereas in the private hospitals, the rural areas increase is much more accelerated as compared to the public hospitals, isn't it? So what that really means is that, if you remember, when I was studying MD, I was under the impression that cesarean sections were a problem of the elite. It was mostly education. It was mostly high income group that opted for cesarean sections. But if you see now, it's actually growing more in rural areas, and in rural areas, especially where it is increasing, is the private hospitals. And not just that, that means that it's the rural private hospital where you have to pay money from your own pocket. There is no health insurance, or there is no government that is paying for you. So it is also causing a lot of health system burden or out-of-pocket expenditure, to be frank, more than health system burden. So we tried to look at what are the patterns, and it's again based on the HMIS data, and there are n number of patterns that are being revealed, but it's not really uniform. It's not really clear. Yeah, there is definitely an increasing trend by time in every state and in every district, but also there is variation in between states and within states as well. So in order to make sense of this mess of data, we thought GIS can really give us some insight. So that is where we geocoded the data and we presented. And once we geocoded the data and looked for clustering, it really showed that there is a clear pattern of hot spots and cold spots, in the sense that the central India was really a cold spot, whereas the north and the south had higher clustering of cesarean section. This is only for NFHS 5 that what I'm presenting, but it is also true if you look at the left side table. You can see that the p-value is significant, highly significant for everything. In fact, not just for cesarean sections, but also for institutional deliveries. But then, if we further break it down, in the sense that if we do a hotspot analysis for public hospitals and private hospitals, the patterns are different, in the sense that on the left side, the public hospitals, the major drivers of cesarean sections in government hospitals are happening in the state of maybe the North Punjab, J&K, and also in Telangana and Tamil Nadu and Karnataka. And there are cold spots in Uttar Pradesh and Central India, the North Belt also. But if you look at the private hospitals, the major drivers of cesarean sections in this belt of Andhra, Odisha, West Bengal, to an extent the northeast belt, is the private hospitals which are pushing the cesarean increase. And this is really, really valuable information for a policymaker to see that, okay, if at all I need to curb cesarean sections, where do I need to do? It's not just where, but in which hospitals, in which districts. So that's also quite relevant. And now I was talking about HMIS data, and I just I'm showing you an example of the kind of ease we can do things with. For example, I just created a function for doing a hotspot analysis, and then I asked it to create the plots for me, and for the years 11 to 19, and then it created all the plots. And when you're trying to show that the same kind of inference you can get from two different data sources. But not only that, they are also showing the same kind of patterns that also validates the use of this routine health data. And then I'd like to, I know we don't have much time. This is again talking about the built environment. This is some of the work that has been done with the help of this work done by one of our PhD colleague, Dr. Joanna. She was looking at the Landsat images and this sequential raster images from multiple satellites. She was using the Bhuvan satellite portal. If you know, ISRO has a geo portal that provides us the Indian remote sensing satellite series data that is freely available to download from Bhuvan. But you need to again do it manually. You need to go and click, and it does not provide an API now. But Google Earth Engine has a better way of accessing data. I will not support Google Earth Engine because it is not free and open source, but it has a very huge wealth of data that can, if you really know how to get it, you can just directly get it on your computer. You can study migration across Kerala, but this is work done by Dr. Tijo, who is also a PhD scholar here. And this is Dr. Gurpreet's work, who was trying to model the incidence of dengue, and he worked on the spatial temporal models, and he tried to forecast dengue for the state of Punjab at the block level. And the 150 blocks that you can see, and this is a standardized incidence rate that is trying to create the plots for looking at it temporally. This is an example of some of the early work that we did in terms of COVID-19. So first what we did was we created a dashboard for India. And then based on that learnings, we customized it for the state of Kerala. It was very easy. We just, write the algorithm and, we converted it. And these are all, I know this is quite old information, but it's also possible to actually create, sorry. Yeah, anyway. Sorry about that. Yeah, I'll skip these slides. Yeah, we could also create dynamic reports by just specifying the state and district. You change the state and district, it all does the analysis and creates a report that can easily be sent to the concerned this thing. And yeah, it's always, this is again, we use the Google mobility data for detecting patterns and things. Yeah, I will, yeah, this is some of the work that we are doing now. We're in the process of working with the Society for Vascular and Interventional Neurology, World Stroke Congress, and University of Florida, where we're trying to map the access to stroke centers in India, and we're trying to generate look at the distribution of all stroke centers, and also trying to see where the inequities are. These are the areas where, if you look at it, almost 80%, 75% of India lies in the red zone. And this is again 4 hours time zone. If you look, this is called an isochrone analysis, but this is not really. This is some of the early. I cannot show you the recent ones because it's up for publication, and we're on our embargo, so we cannot share the results unless Lancet allows it. Yeah, this is just for Kerala state. This is looking at the access to IVT and EVT centers. One of them is endovascular thrombolysis. One is for thrombectomy and one is for thrombolysis. Yeah, and we also conduct a number of workshops. I think I'll stop the what do you call it, case studies, but I would like to just end with the we do have case studies for most of, all of these point pattern data, aerial data, raster data, network data, where we worked with Pondicherry state governments, and Dr. Anand was working on his PhD work, looking at crash and fatalities in the state of Pondicherry. Yeah, and we are also having a project with the ICMR. We are tasked with looking at the COVID-19 testing data set, which can be called bigger than the big data, because it has tests of over 100 crores tests of Indians, and we did work on that, but I cannot again show that with you. Yeah, there are a number of challenges in the future directions. There are some immediate challenges, fresh requirements that we need, and we need alternative sources for completeness and validation of data. Just like I was showing, we were able to validate this NFHS with the HMIS. Only then people really looked at, because otherwise, if you're only showing NFHS data, then they say, okay, this could be something because of something else. But when you're showing multiple data sources and validating your results, then people cannot, ignore it for much longer. Yeah, there is a data can no longer be a point in time. It has to have a temporal nature, and much of these decision tools and solutions have to happen in real time. So this has to have some automated methodologies involved. And in the future, it is going to happen in such a way that we'll be creating digital twins of our cities, our populations, and we are going to live in virtual worlds also. And there is a lot to learn, but as a field for community medicine, we have to take it forward. Otherwise, people from IT will come in and do something that they don't really have the domain expertise for. So we as domain experts have to rise to the challenge. I think I'll end here, and the slide, I'll put up the slides in this link. I'll share that link with Dr. Nitin. He can share it across. Other than that, just a couple of things. We have if somebody is interested in having some kind of training for this kind of analysis, maybe not the spatial thing, but before spatial, we have to have some bare minimum understanding. So we are conducting a national workshop on health data analytics at AIIMS Kalyani. The dates will be somewhere in 4th to 7th of December. And if somebody is interested, you can register. You can always message me in LinkedIn. I'll share these slides with you. You can just click the website link and you'll get them. Yeah, thank you. I'll stop here. I'm sorry for taking too much time.
Yes, thank you so much, Dr. Arun, for taking us through your presentation. And Dr. Arun has been speaking for last 1 hour and 50 minutes, to be precise. I think you can have a sip of water.
Yeah.
You deserve one. So thank you so much. We have 49 individuals who are with us for such a long period of time. So thank you so much, Dr. Arun, for sharing your valuable knowledge with us. And you have given us a wonderful overview of what is spatial epidemiology, spatial analysis. And you are the right person to share this knowledge, because you have been working consistently on various projects. And you have given us a wonderful glimpse of what work and the quality of papers you have been publishing. So thank you so much. And I have put up post-test quiz in the chat box. Please answer it. Okay, copy the link if you are not able to answer right now, and you can do it later as well.
I have one request, Dr. Nitin and everybody. You can just give the negative feedback as well. I don't want all the positives. We want to learn, so you can. I know it's too much, but yeah, you can be frank in your comments. That's a request.
Yeah, Dr. Arun is a very kind person, and he doesn't mind even negative feedback. So you have positive, negative. We are welcome all kinds of feedback, and please do give us your valuable feedback. In the form, there are 2 questions: what went well and what you didn't like about the session. So please do give us your valuable feedback. So, anybody would like to ask question? We are open for question, and then yeah, you can give us valuable feedback as well. It's too much late. It's 8:53 on my watch, and people would like to go and have their dinner. Dinner must be already served on your table. So if you have any questions, you can take 1 or 2 questions, or you want to give us feedback, that will help Dr. Arun. He has taken so much trouble to prepare for this class, and he invested so much energy. I'm really impressed with the energy level of Dr. Arun, that he could go on for almost 2 hours. Thank you so much. Okay, he could have spent this evening with his family, but rather he chose to spend this evening with us. So thank you so much, Dr. Arun. Yes, anybody would like to give any feedback? Otherwise, we can call it a day. Please use the feedback in the post-test quiz, and in that we have inbuilt feedback form. Yes.
Dr. Hina was, you asked something about data sources as well, right? And books. Yeah, I think what I'll do is I'll add that in the n number of data sources actually. First thing is you can go for non-spatial data. That data.gov.in provides n number of Indian related data. But for remote sensing, I think Bhuvan is a good source. If not, I would suggest if you are, if you know how to